Okay, here we're going to define the force between two parallel wires. Okay, why do we need to find the force between two parallel wires? Because if you look at any transmission lines or distribution lines, power lines I'm talking about, okay, there are always parallel wires running around. Okay, so we want to find what is the force between those two conductors. Now if we look at here, I current is, assume that both currents are going up. Okay, now because of the current flowing in conductor 1, this is conductor 1, this is conductor 2. So because of the current flowing in conductor 1, there is always a magnetic field around this conductor that we can find out by using the right hand rule. So it's going in anti-clockwise direction. So if I represent that in vector format, so the magnetic field is going into the paper here, it's coming out here. Is that right? So magnetic field is going into the screen on the right hand side, coming out on the left hand side. Now if you look at here, so I'm going to extend this magnetic field because of this conductor. Okay, now if you look at conductor 2, okay, conductor 2 is placed in a magnetic field. That magnetic field is B1. What is that B1? B1 equal to mu naught I1 over 2 pi r, where 2 pi r is the distance between these two. Now that B1 is a magnetic field at this point, at where the conductor 2 is placed, equal to mu naught I1 over 2 pi r. Now conductor 2, it's a current carrying conductor. It is placed in a magnetic field. For sure it is going to experience some force. What is that force value? F equal to B I L sine theta. So here theta is 90 degrees because if you look at the conductor is parallel to the screen and magnetic field is perpendicular to the screen, so it is going into the screen. So there it's 90 degrees, theta is 90 degrees in this case, so we can ignore that. Sine 90 is 1. So F equal to BIL. Now I'm going to pull that L to the other side. So let me take this as F2, force 2 per unit length, equal to B1, and this I is I2 because of the current flowing in that second conductor. Now I'm going to substitute B1, so F2 over L, force per unit length, equal to mu naught I1 I2 over 2 pi r, force per unit length. That's a force on that conductor because of the magnetic field in conductor 1, produced by the conductor 1. Now what is the direction of that force? So if you use the right hand rule, perpendicular to, all three fingers perpendicular to each other, thumb indicates the force, middle finger indicates the magnetic field direction, forefinger indicates the current direction. So current is going up and magnetic field is going into the board. So for sure, so current is going up, magnetic field is going into the board, for sure it's going to experience a force in this direction. Okay, so this conductor is going to experience a force in that direction towards the conductor 1. That's a force 2 per unit length. Same way, if you look at this is this is F2. If you look at F1, so magnetic field by conductor 2, so current is going in, going up, so it's going to, magnetic field is going to be something like this. Okay, now current is going up, magnetic field is coming towards you. You can see that force is going to be in that direction. So F1 per unit length equal to mu naught I1 I2 over 2 pi r, where r is the distance between those two conductors. So based on this, you can see if same amount of current is passing through the two conductors in the same direction, then they're going to attract each other. If currents are flowing in opposite directions, so here is I opposite direction, then they're going to oppose each other. Why are we saying current is flowing in one same direction and flowing in opposite direction? So if you look at any closed circuit, I mean that's what we learned in the previous chapters. So here is a resistor. I always indicate these two conductors in a distance, but in reality what happens, here is your resistor, these two wires are going to come in the same conduit. Okay, it's going to be connected like this, right? So these positive and negative conductors are side by side. So here if you look at the first conductor, current is going in one direction. In the second conductor, current is coming in the opposite direction. So these two conductors are running parallel for long distance. So that's the reason here current is going in the opposite direction. So when the current is going to go in the same direction, sometimes the same conduit is going to run for different elements or different resistors. So now all these three conductors are flowing in the same direction. Okay, so if current is flowing in the same direction, then those two conductors are going to attract each other. If current is flowing in opposite direction, then they repel each other. Thank you.